because there's this overlap, and you've counted this place twice. You've counted it in the probability of A and in the probability of B. So you'd also just have to subtract this. Okay? So that would be, that's bad. A little bit of improv. So we'll write 4B, right? So this is saying the probability that one of them happens, at least one of them happens, right? So it's the sum of A and the sum of B minus their overlap. But the real thing, the important thing is what is this? What is the probability that they both happen? And that's a little difficult to answer straight away, which is kind of in this region here, because it depends exactly on their dependency. The naive student might write down this, but this is only true if they're independent events. In fact, you can just make this the definition of independent events. So we're just going to forget that because we want to be more general than that. So let's consider for a second that A happens. Let's do that. Let's consider for a moment that A happens. In that moment, your universe collapses. And now you have A, and this section, which is what's left, is B, which was formerly the intersection of A and B. So the probability that B happens in the universe that A happens is simply this number that we had before, right, which was the intersection. Except we have to rescale that number, and we're just rescaling it by our new universe. Our new universe is the universe in which A happened. So you just rescale that number. Right? So this number here, which was is the intersection of A and B, in the universe where A happens, this is now the probability that B happens. So the probability that B happens in the universe where A happens is the joint probability in the first universe, and then you just renormalize. But there was nothing special about that occurrence, so we could have done this the other way, right? And we could just write now the probability of A happening in the universe where B did happen is going to be the same thing. Just their overlap in that original universe renormalized. And now if you're already familiar with the answer, where am I going to write it? I'll write it here. You can equate these two things, right? Because they share this common term. And then you just have this thing. And this is the statement of conditional probability. Okay? This is not a B thing, it's not an F thing, right? It was mentioned this morning that, we're just familiar with conditional probability. There it is, conditional probability. Why does this matter? It matters because in science, we collect data, and this is also not a B or F thing. We collect data, and we basically are dividing the universe into knowable and unknowable quantities. We're always making an inference, right? There's a finite sample of things, and we want to know the population mean. It's an abstract thing. It's something that you can only get at with infinite number of samples or something like that. So now we have to make the important choice of saying which of these is the knowable quantity and which of these is the unknowable quantity. So I'm just going to reassign A and B to be data and model, let's say. So we're going to take this equation and just recast it in terms of the data that you observe and the model you have for that data. I'm doing this very sloppily, but I don't want to take up too much time. So I've just rearranged the terms and put them in different quantities. The model, or the parameters for the model, or whatever the abstract quantity is, the unknowable thing, that's usually what we're trying to answer for. We want to know what is the mass of the neutron star, right? No matter how much data you get, you can only be so certain about it. Even if you take the philosophical interpretation that there's one true value. That's a matter of philosophy, okay? Just how you calculate, nobody argues about that. And it's all legitimate calculation. It's just, it's not really important to make a distinction of philosophy. But what's important, though, right, is in some of the more classical methods, people just look at this thing, right, and then they characterize this distribution, this probability distribution, which is the probability of the data given the model. And then you get these classical kinds of, referred to as credible intervals, which are basically fixing the model and varying the data, which, again, you can have an interpretation about the, do you like doing that? Do you like coming up with new samples of data that you didn't observe? Or do you want to kind of just take the data at face value and make an inference on that data? And coming back to my original point or statement that in science the thing we care about is not this, it's rather this, is saying exactly this, right? We're not looking for the answer to the question, what is the probability of observing our data given a model? We want to know what is the probability that the value we think is the true value, and it may be a true fixed value, is that value. And there's no disagreement about this not being able to answer the question, right? So the fudge thing that usually happens now, and there was a lot of talk about the importance of the prior, this thing here. The fudge that happens is, we just say this is 1, and then you're done, right? You basically say this is non-informative, it equals 1, and then you're back to the answer to your question. And all of the classical frequentist techniques are still legitimate, and they still answer the important questions that go along with getting the parameters and the description of the likelihood function. And then, if you're forced into the situation where you have to answer this question, you just say, this is 1, and you're done. So there's a really artificial boundary between Bayesism and frequentism, and I want you to walk away with the image that that's not a real dichotomy in science. I've heard about it for the last 10 or 12 years, and I've yet to see it be a real problem. And I think that's everything. Yeah, so I wouldn't label myself one or other thing, but coming back to that point where sometimes in other areas of science you deal with a really small number of samples and you can't repeat experiments. That forces you into a situation where you basically have to fix some parameter as being the best parameter and then simulating very many data sets that you think could be realistic data sets if you could do the experiment many times. And that allows you to get a better description of this thing. But you could sit around with your friends and argue, faking data or simulating data, playing the game of where you know what the answer is already, that's not real life, and that's highly subjective as well. So the objectivity-subjectivity debate is also just something that's outside of science, I think. Not outside of science, but in science, everybody playing the game, I think, agrees that there are unknowables, or even it's in the limit of the far future that you can know things with any real certainty. So, therefore, in science, we're really interested in this. And you just have to deal with Bayes' theorem in order to do that. You can get the answer to this using classical frequentist methods. And then, all this MC stuff gets labeled Bayesian just because it fell out of that community. But it's not really, that division is not a real important thing. So that's all I wanted to say. And I will take questions, but it doesn't have to be now.
Questions?
What do you mean by the probability of data and probability of model?
Ooh, yeah. Okay, so that was explained more this morning. So first, I'll give more vocabulary. So the probability of the data given the model. This was called the likelihood function, especially when you're considering it as a fixed function of the data thing. And this probability of the model, or the parameter values, is referred to as the prior, and he referred to that this morning. So this, if you're talking if you're using the vocabulary of beliefs and things like that, this is your prior knowledge of the model being true or the parameters taking a certain value. So these are all just distributions. And this likelihood thing, the most important one that I mentioned yesterday in the talk you've heard about earlier, is that we want Gaussian distributed uncertainties. So we have some model for what our times of arrival should be. We have our data. We subtract the two things. We want what's left to be Gaussian distributed. So this likelihood function we want and usually use to be a Gaussian function. And again, we won't talk too much about this term, usually called the evidence, because you only need it for, we don't only need it, but it's most important when you're doing model comparison. And this was something that I don't think was talked about this morning, the difference between parameter estimation and model selection. Very important difference to talk about. And it's really there that I think people who might align themselves somehow with being frequentist, which I don't really think is a thing, might take they might take issue with, because model selection nowadays almost always happens in a Bayesian framework, because I'm sure you've heard about all this p-hacking and reproducibility issues. That all comes out of the fact that model selection, basically frequentist techniques for parameter selection were used to do model selection, and that's bad. Okay.
I disagree, but I agree with you in the way that I don't think it's the nature of the statistic. I think it's more that in frequentist statistics, it's very easy to forget the assumptions you're making and not put them into your article and assume that everyone else has understood your assumptions just as well as you have understood your own assumptions, which makes reproducibility much harder with frequentist statistics.
Okay.
I agree with you completely that there really is no divide if you look at the statistics. It's just that Bayesian probably forces you to report much more about your assumptions than frequentist.
But
lose
but it's like you said, nobody disagrees about. There's no dodging the question of what are your assumptions, what is your prior belief, or you don't have to couch the discussion in terms of belief. Max Tegmark has this famous quote, which is kind of vulgar, about quantum mechanics, which is that Copenhagen or multi-universe or whatever, doesn't matter, shut up and calculate, because you just choose a tool from your toolbox that's appropriate for the problem and you arrive at an answer. You're clear with what you did. This was the point also this morning, was understand your tools, choose the tool appropriately, and there are no there's no two teams and they're competing. So and this morning I think the probability of the data, the likelihood that was being used, one of them was a binomial distribution, if I was paying attention. Isn't the binomial a subset of beta? Maybe. I don't know. I'm not a statistician by any means, so maybe I shouldn't be up here. But any other questions? All right, later.